In this lecture video, I will be going over the hydration reaction of the alkynes. So very similar to the alkene, the alkynes can also undergo hydration reaction as well. And we have seen already in the previous chapter that there are three different ways how to do hydration reaction of the alkenes. When it comes down to the alkynes, we will discuss two methods to do hydration reaction of the alkyne. And the first one is the acid catalyzed hydration. And then the other one that we will also be discussing is the hydroboration oxidation. And that will be another way of doing hydration reaction of the alkyne. But here is one of the very distinct difference between the alkyne and the alkene in the hydration reaction. So in the case of the alkynes, once we have done the hydration reaction already, then the alkyne will then be converted into something that we call an enol. And the enol will then undergo a further step that is then referred to as the tautomerization step. And the byproducts or the products of this tautomerization step right here is that the enol will then be converted into either an aldehyde or a ketone, dependent on what types of enol it is. And this tautomerization step right here can be catalyzed by acid or base. It can also happen on its own, but at a much slower rate. So acid and base catalyze would speed up this tautomerization step right here. So now let's talk about the acid catalyzed hydration and get into this tautomerization step right here in great detail. So when we do an acid catalyzed hydration of the alkyne, then what we have discovered is that it will undergo a Markov addition, in which the OH group is then added to the more substituted alkyne carbon to produce an enol. And the reason why this undergoes the Markov addition is quite easy. When we draw the reaction mechanism, this is simply produced. This product right here go through a more stable carbocation intermediate, which we'll see in a little bit. And in order for this reaction right here, this hydration reaction of alkyne to go faster, then we need to basically have acid and sulfuric acid, and also hydrogen mercuric sulfate. So this is then used as a catalyst to speed up the reaction right here. So that would have been discovered experimentally. And so the product would then be the enol. And this enol right here then further undergo the tautomerization step into a ketone or an aldehyde, dependent on whether we have a terminal alkyne or the internal alkynes. So now, let's now talk about the terminal alkyne first. When we take a terminal alkyne, reacting this with sulfuric acid and water and mercuric sulfate, then so again this would then be the hydration reaction right here, and we can see that water would then be added to the more substituted carbon, which is this carbon right here. So this OH would then be added right there, and the hydrogen then added to the other less substituted carbon over here. So this is then called an enol. Now the reason why this is called the enol is because of the following. In here refer to a double bond, or here refer to an alcohol. So an enol is basically when we have an alcohol and an alkene right next to each other, as what we seen up here. So this is called an enol right here. Once the enol is been produced already, now it is not a stable substance in the way that it is. So the enol are actually not stable, but it will undergo another step that you call the tautomerization step. And here is what this tautomerization step is all about. So what happened is that this lone pair electron on the oxygen is then donated down. And now the electron is then given to this carbon, and this carbon then come in and grab a proton. And this is why that we need to have acid to catalyze this reaction right here, or at least the mechanism in the acid catalyzed tautomerization. And so the product is when we would then have a double bond right here, and now the carbon is then added to this carbon. So here in this case right here, we are producing a ketone. Now, so I'm skipping the last proton transfer step right here to deprotonate this carbonyl right here. But after this, after the extra proton transfer step, then this will be the product right here. And so here again is the mechanism of that tautomerization step. Once we produce this already, here is the last proton transfer to now convert this into a carbonyl. And in this case, we are producing a ketone, a methyl ketone. And if we were to have a internal alkynes, then we can also do this reaction as well. However, it wouldn't be a useful reaction unless the R1 and the R2 group, so the two alkyl groups that connected to the two alkyne carbon, are the same thing. And the reason why is that what happened is that either this carbon right here can become the enol and further tautomerize. So if we were to have different R group here, then we'll be forming a mixture of two different products with almost equal yield, and that would result in this reaction right here not having that good of a selectivity, and therefore the reaction is not as useful. But if R1 and R2 were to be the same thing, so it does not matter where this carbon become a carbonyl or this carbon become a carbonyl, the two products would then be the same thing. So therefore that and when this type of reaction would be much more productive. So first, when we take this internal alkyne right here and react this with again sulfuric acid and water and the mercuric sulfate, then first we can either have the OH group on this carbon right here and the hydrogen to this carbon, or the other product where the OH group is added to this other carbon and now the hydrogen is on the other carbon. So both of these are the enol right here. And once we have produced both of this enol already, it is then followed by the tautomerization, where now they be converted into the carbonyl derivative. So here in this case right here, this is now a ketone. And in this case right here, we'll also be producing this ketone right here. So if R1 and R2 were to be the same thing, then these two products right here would then be the same. But if R1 and R2 are different, then these two products right here would then be different. And both of them get formed in roughly the same percentage. And now let's try some of this product right here. So in this case right here, if we were to now have this triple bond reacting with this, what will happen? So here in this case again, so we can see that the first we will be doing hydration reaction where the more substituted carbon will have the OH connecting to it, right? So that would then be the intermediate product right here. So let's draw its chemical structure out. So initially, this is what we will be producing. This enol, and once we have produced this enol already, it would then undergo tautomerization, and we still have sulfuric acid in this solution right here to catalyze this reaction. So this is why we don't have to add extra acid to make sure it can undergo tautomerization. And now let's pick up the proton from the acid, and so in the end, this carbon right here, the more substituted carbon would become the carbonyl. So therefore, the product of this reaction will then be as follows. And in this case, we are producing a methyl ketone. A methyl ketone is basically a ketone in which that one of the all alkyl group is a methyl. And now if we were to do the same reaction with B, then in this case right here, this is an internal alkene. So we can either have this carbon become a carbonyl or this carbon right here become a carbonyl. But because this molecule right here is symmetrical, so therefore either one, it would then be the same thing. But again, so the products is basically when we have so this can become a carbonyl, and now this carbon right here and that will be this product right here. And now we're going to go over the other hydration reagent of the alkynes. So this reagent right here is the hydroboration and oxidation reagent. Now we have seen this reagent already in when we were learning about the hydration reaction of the alkene, in which that it produced the anti-Markov products. So here in the case of the alkyne, it would do the same thing. So this would then be adding an OH group to the less substituted carbon. So basically this is the anti-Markov product right here to produce the enol. And again, this enol right here have the OH group connecting to the less substituted carbon. And this enol would then further tautomerize as well into the corresponding aldehyde or ketone. Yes, if we were to have a terminal alkyne, then this would then tautomerize into a aldehyde. Versus if we were to have an internal alkyne, then it would then tautomerize into a ketone. So this is how the starting structure of the alkyne would produce different types of products. And now let's go over the mechanism of this reaction right here. And it's actually very similar to the mechanism reaction of the alkene as what we have seen before already. So when we take our terminal alkyne and react in this with BH3, so this is the oxidation step right here, or the hydroboration step right here. So here in this case right here, we will then see that first this act as a base, and this come in and attacking this boron right here, and producing a carbocation on either this carbon or this carbon. And it would be better to produce the carbocation on this more substituted carbon. And therefore the hydrogen from this BH3 would then come over and attack in this carbon right here. So in the end, we have the hydrogen being added to the more substituted alkyne carbon. And the other carbon would then become this BH2 group. And we can see that this can really happen 2 more times with 2 other triple bonds. But we're not going to get into that mechanism and it get too complex down the way. And so once we have this product already, we can now do the oxidation by using hydrogen peroxide with sodium hydroxide. And now this would come in and would have the OH group replacing this BH2 group right here. So at the ends of this oxidation step, that's the product that we will have. And now this is the enol. And this enol now would then tautomerize and would then tautomerize into a ketone. So in this case, the electron is donated down, and now this come and grab a proton. And again, this have to be either acid or base catalyzed. So either acid or base would work. And here is the mechanism of the base catalyze right here. If we were to have base, and in fact, in this reaction right here, because we have sodium hydroxide, so once this oxidation step right here has happened, it will also do a tautomerization as well, because this reaction, the reagent should have base in it. So the base would come in, pick up this proton right here, and now that would then take this electron down, and then that would then come here and pick up the hydrogen. So first, we'll produce this, and this is called the enolate right here. So an enolate. An enolate, when we have, can come in and pick up a proton from water. And in the end, this will then become the aldehydes. So that's what happened right here. If we were to have the terminal alkyne, it would then, after the tautomerization, would then become an aldehyde. So please keep that in mind. Versus if we were to have the internal alkynes, then the reaction would, again, as to what we have seen before in the other reaction of the alkyne, then now either the alkyne carbon can become a carbonyl. So therefore, it wouldn't be a useful reaction, right? So, and whenever we have the internal alkyne, we actually do not react this with simply this BH3. And because the reason is because this hydroboration reagent right here is non-selective. So we can actually either convert this carbon right here, convert this carbon into an enol, or this into the enol right here. And this would then produce an equal mixture of 2 products, and therefore make this reaction here not very useful. But instead of using BH3, we actually have discovered there's all the types of boron reagent out there that actually will allow us to control the regioselectivity in these types of reaction. So basically, we'll be using the dialkyl boranes. Dialkyl boranes is basically the types of boron reagent in which that now it does not have 3 hydrogen on it, but only 1 hydrogen, and then the other 2 group are actually an alkyl group. And a lot of times the alkyl group are big groups to make them bulky. And because the more bulky the reagent will be, then the more selectivity that they will provide. So this group right here is called the amyl-borane, and that's how we would abbreviate them. And we can also have this reagent as well. In this case right here, then now there is a ring system in this. And here in this case right here, we call this 9BBN. But again, it have one hydrogen on this borane right here. So the key thing to this reagent, both of this reagent right here, will then be they are steric. And because they're steric, they actually would favor one of the alkyne carbon over the other. For an example, when we take this alkyne right here, so this is an internal alkyne, and now they're not equally substituted. So when we react this with either this reagent right here or 9BBN, then we would then see that the hydrogen will actually be added to this group right here. And then the rest of the other groups, so this 9BBN or this SiA2H right here, will then be added to the less substituted carbon. So that's the key aspect of it, this reaction right here. And in which because this group right here, bulky, it will not be added to this carbon right here. And again, this is due to steric hindrance. So therefore, the products of this reaction, let's say that if we were to be using this reagent right here, then now we'll be having this product right here. So the boron there, and the Si, the two alkyl group right here, and the isopropyl group over here, and the hydrogen right here. So the hydrogen is being added to the more bulky carbon, or the more substituted carbon. And followed by the oxidation step. So the step number 2 with the hydrogen peroxide. Then now we will see that this would then become the enol. And this enol then tautomerize in the presence of base. So the base will then come in, pick up this proton, and this will come in and tautomerize and pick up the proton from water and convert this into the keton. And that will be the product of this reaction right here. So now we have a keton. And again, the key thing to this reagent is that we don't want to be making a racemic mixture where we can have this carbon become a keton, or the keton is on this carbon right here. So that's the whole point to using this dialkyl borane right here. So that way they can be steric. And now the group here will then be added to the less substituted alkyne carbon. So let's now try some of this example right here. So if we were to now have this reagent right here, this alkyne reacting with these two reagents, let's see what would be the major products. So here in this case right here, when we treat this with 9BBN followed by the oxidation with the hydrogen peroxide, then again, we would then see that this would then basically have the N-time copper addition with the OH group would then be added right there initially, and followed by the tautomerization. So here in this case right here, we will be making our aldehyde. So the product of this reaction is as follows. Now initially, that's what we have right there, and followed by the tautomerization step, and we would now be having this product right here. So this is the aldehyde. Versus if we were to now do this reaction right here with sulfuric acid and water, and in the presence of mercuric sulfate, then now we can see that this would then be the Markov addition right here, where the OH would then be added to the more substituted carbon. So here in this case, that's what will happen. and followed by the tautomerization step will be making a methyl ketone here in this case. So the product of this reaction right here will then be as follows. So that will be the product of this reaction. So please note of the differences between these two products right here. One reagent will give us this product, while the other one will give us a different product.